Today I'm looking forward to discuss principal component analysis, which is a great dimensionality reduction technique. Say I go to a zoo and I want to take a picture of these animals. And of course I cannot ask them to stand in a line. I take out my camera, I take a picture in this angle. I'm not happy with that. Then I walk over and I take one more picture, and that was not satisfying as well. I walked little more and I took a picture from this angle. Yes, this is the right angle, or this is the best shot I could get because I was able to capture most of them. In short, if I keep my camera in such an angle that I'm able to capture most of them and I'm able to get most information, that gives me highest value. In this shot, the variance is not high, or in other words, this picture has overlapping pictures of the animal. On the other hand, if I keep my camera in this angle and I take my picture, then I have the highest amount of variance, or I'm able to get the highest amount of information. This is what is principal component analysis, where we are able to take a picture of our data point which gives the highest amount of information. Let's move on to next example. In this example, I have a room where I want to measure the temperature, the light intensity, and the humidity. And as my humidifier is on the floor, I see my humidity is high down the y-axis and it's low as I move up. On the other hand, the light and the heat are more as I move along the x-axis to right, and they are low as I move to the left. So this is a three-dimensional problem, or I have three values for every coordinate or every location in the room. Wait, do I need three parameters to solve this problem? Maybe not. I can do this problem with two, because both the light and the heat move hand in hand together, or they are highly correlated variables. So I can have one average value and I can call it as incandescent measure, and I can solve this problem in 2 dimensions instead of 3. Sounds good. Let's move on to next example. This figure may be familiar to you. Back in school days in physics, we have seen this object on an inclined plane on which we have various forces acting on. The normal force, which is perpendicular to the inclined plane, and then you have the friction, which is parallel to the inclined plane, and the gravity, which is straight down. These forces are in different direction. How do we deal with it? And the x and y coordinates are itself different from the normal and the friction. So why don't we rotate the coordinates, and by which the friction is on the x-axis and the normal force is on the y-axis. But now the challenge is with the gravity. So the gravity can be broken up into two components, one in x direction and one in y direction. In that way, what's going to happen is I have forces all in x and y coordinate in 2 dimensions. Now I don't want to double count the gravity, so I can remove the primary mg force and leave behind the 2 components. Now we were able to transform this data into 2 dimensions, and which makes our life easy to solve this complicated math puzzle. Now that we have seen few examples, let's open up the hood and look inside. In any principal component analysis, we do data transformation. And in this particular example, I have taken a simple 2-dimensional problem, and the transformation matrix is 3, 4, 4, 9, which is a symmetric matrix. That means across the diagonal, the numbers look the same. When you look from across the diagonal, 4 and 4 are symmetrical. Now, what happens in this transformation is every point on the left hand side, x or y, gets transformed into 3x plus 4y and 4x plus 9y, and I refer that as capital X and capital Y. So based on our data point, this transformation matrix comes up, and then based on that we calculate what is eigenvalue and eigenvector. So we are going to see that logic. Before that, every point on the left gets transformed to y. So if you see, the point 0 and 0 will get transformed to 0 and 0 because there is no shift. But every other point will also get transformed. But the catch is, the circle, the unit circle on the left creates a circle on the right as well, but that is stretched by certain value on the right hand side. Now, looking at the equation of this transformation, we have a matrix, we multiply that with a vector that gives you the same vector multiplied with a scalar. And the vector is called the eigenvector and the scalar is called the eigenvalue. So there are two possible values for which this matrix, this equation is valid. And that when you calculate, you get as eigenvector 1, 2 and minus 2, 1 with a value of 11 and 1. So if you want to convert this two-dimensional problem into a one-dimensional problem, you want to eliminate one of these. Of course, I want to eliminate the one in red color because the one in blue has a magnitude of 11 and I get maximum value or maximum variance by retaining that. So my blue line will give me the highest variance, and that is the one I want to keep if I want to convert this into a one-dimensional problem. So that shows which is the one to keep and which is the one to drop. Now that we know in general what is PCA, let's look into the whole process in one screen. Let's take an example where I have 5 features, F1 to F5, and this 5 feature is way too complicated for me and I want to convert them into 3 dimension. How do I do that? First, I want to do exploratory data analysis and prepare the data. And I also want to do a Z transformation because sometimes we have variables with high value and some of them with low value. We don't want the high value ones to dominate over the low value ones. So I want to do a Z transformation and bring all of them on one scale. Now this 5-dimensional data is very challenging to solve with. So what I want to do is I want to transform them into a covariance matrix followed by eigenvalue and eigenvectors. If I decide to go with 3 dimension, then I can drop the bottom 2 because the eigenvector 1, 2 and 3 have the highest value because the eigenvalue are the biggest for those and 4 and 5 are the smallest. That being said, I cut off after 3 and drop 4 and 5 eigenvector and the value and keep only the top 3. So now basically I have converted this 5-dimensional problem into a 3-dimensional problem. So that being said, now I can solve this problem with this graph and I can visually understand and I have 3 dimensions which I can use for my analysis. With this, I am done for this video and I thank you for watching this video. Have a nice day.